Now we're going to take a look at parent functions and transformations. On this sheet, we have a summary of all of the different types of transformations that we'll see. Today we're going to see them separately, and tomorrow we're going to look at combining them. First of all, our example parent function is the absolute value of x. For vertical shifts, you will see it outside of the function. So for all of our parent functions, there is something that we're doing to it. We're squaring it, putting it in absolute value, etc. So if it is outside of that, then it's a vertical shift. If it is grouped with the x inside the absolute value or the power or the radical, then it is a horizontal shift, and it's in the asylum, so it's not normal. If it looks like a right shift, it'll actually be shifting left and vice versa. The reflections we'll see tomorrow. Vertical stretches and compressions, again, will be outside of the function, and it will be multiplication. If you're multiplying by a value greater than 1, it's a stretch. If you're multiplying by a value between 0 and 1, it's a compression. And of course, horizontal compressions are grouped with the x and are not normal. If the value is greater than 1, it's a compression. If the value is between 0 and 1, then it's a stretch. Starting off with a quick recap of what the parent functions look like. A parabola, the x squared function, has a critical point or a vertex at 0, 0. Those will be important to remember as well. We'll use those with our transformations. The cubic function, I've also heard a lot of students refer to it as a snake, also has a critical point at 0, 0. The square root or radical function is half a sideways parabola. Again, the critical point is 0, 0. The absolute value is a sharp V with a critical point at 0, 0. The inverse function has asymptotes along the x and y axis. So I call 0, 0 the critical point, even though the graph does not go through 0, 0, but that's where the asymptotes meet. The inverse square is the same type of critical point, but it's above the x-axis entirely. And finally, our step function. This is the one that has a solid circle at 0, 0, an open circle at 0, 1, and continues in that pattern, both forwards and backwards. I call this critical point 0, 0 because that's where I start my first step and think about the stretches or compressions from there. Our first translation, we want to identify the critical point. So we think about the fact that the critical point for all of our parent functions is 0, 0, and we want to identify how this graph is shifting. We have a -1 grouped with the x, which means it's not normal, so it's really going right 1. And we have a +3 that is not grouped with the x, so that's a vertical shift, which is normal, so we're going up 3. Domain and range for visual people, it's a lot easier to see once it's graphed, so we can come back to that part. To get this graphed, we want to substitute some values into the parent function. Our parent function is 1 over x squared. Get rid of any adding or subtracting. When we get into compressions and stretches, we'll get rid of any multiplication. Make the function as simple as possible without getting rid of powers, because that's not a transformation, that's part of the parent. So we'll evaluate all of these points. 1 over -2 squared would be 1 over +4. 1 over -1 squared would be 1. 1 over 0 is undefined. This is where the asymptote of the function occurs. That was the critical point of our parent function. 1 over 1 squared again is 1, and 1 over 2 squared is 1/4. These second two columns are to think about what is happening to the x and the y value from the parent function to the transformation. In this case, we talked about the transformation being right 1. So we will take all of our x values and add 1 to them, and then we're going up 3. So we will take all of our y values, the parent function values, and add 3. Those are the points that we'll plot to get our new translated function. So we'll take all of those x values that are in the first column and add 1 to them. And for all of the p of x or y values in that second column, we will add 3. This will still be our asymptote. And then we'll plot the points in those last two columns to get our new graph. First, we will graph the two asymptotes for this function. For the parent function, the asymptotes are the x and y axis. For this function, our asymptotes will meet at 1, 3. We'll have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 3. These are the lines that our graph will approach but never cross. Then we can plot our ordered pairs from our t-chart. The second two columns will be our translated function. -1, +3 and 1/4, 0, 4, 2, 4, and 3, 3 and 1/4. Remembering what the parent function looked like, as well as the asymptotes, we can use those to get our curve. Going back to get our domain and range, notice for the domain, if we take a vertical line and slide it along the graph from left to right, we will hit everywhere except for that vertical asymptote. Our domain is x cannot equal 1. For our range, sliding a horizontal line from the bottom up to the top of the graph, we have nothing below the asymptote, and the graph exists everywhere above the asymptote. So our range is y is greater than 3. Next, we have a step function that's being translated. It looks like we're shifting to the right, but that's in the asylum, so it's not normal, so it's a left shift. Outside the asylum, we have a vertical shift down 2. Domain and range we'll look at from the graph again. There's no t-chart on this one because for the step function, subbing in integers is not very helpful. The step function is mostly graphed between values. So we'll remember what the parent function looks like and shift those steps from there. So this time, instead of our first step starting at 0, 0, we'll start at -2, -2. You have a closed circle where the step starts. Steps are 1 unit long, and then you have an open circle at the next spot. Steps are also 1 unit apart vertically, and you can continue from there. We can also make a few steps backwards. Drop down 1, open circle, bar is 1 unit long, closed circle. Make sure you indicate that those steps will continue forever in both directions. For our domain, sliding a vertical line along the graph, where the graph jumps, you have 1 closed circle and 1 open circle. For example, looking here, we will touch the graph just in one place, but we will touch the graph everywhere. So our domain is all real numbers. You can round any number. The range, however, when you're rounding down, the output is only integers. The symbol for integers is a z with an extra bar, or you can simply write integers.